2.2 here. Welcome back. We're doing limits involving infinity, day 1. Okay, so let's just jump right in. First of all, infinity is not a real number. You can write that in. This is important because some people ask questions like, well, what's 2 times infinity, or what's infinity divided by 2, or what's infinity plus 100, or what's infinity minus 300 million. The questions are all flawed. There's no such thing as infinity times 2. Infinity is not a number. It's like saying multiply cow by 2 and expecting to get a certain value, like 5 or something silly like that. So it doesn't make any sense. Okay, the limit of f as x approaches infinity means the y value that the function is approaching as x goes to infinity. So we're no longer working our way inward toward a certain value. We're working our way off to the right and looking at the behavior. The limit of f of x as x approaches negative infinity means basically the y value the function is approaching as x goes to negative infinity. And remember, negative infinity just means leftward indefinitely. Okay, so let's just jump right in. Alright, so here's a graph of y equals 1 over x, where x is not equal to 0. Okay, it's a good function to study. It has asymptotes. There are actually 2 of them. The one we're interested in right now is that asymptote that is horizontal. It's actually the x-axis. But let's focus just on the limit, and then we'll talk about asymptotes themselves. So here we have x going off to infinity. So we're actually traveling along the curve this direction, and you can see that this graph mellows out and approaches the x-axis. This is the y equals 0 line. So since this value, 0, is the y value that the function is approaching as x goes to infinity, we could write the limit as x approaches infinity for this function is 0. As we go to the left, we're on a different branch of this curve. By the way, this is a rotated hyperbola. We can see that we're also approaching x equals 0, or excuse me, y equals 0 as x goes to negative infinity. Okay, now if only this first one had been true, and this side of the graph had looked entirely different or was absent or something, this still would have been a true statement, because we would be dealing with the right hand side of this, and we would still say that the line y equals 0 is a horizontal asymptote. So some people are under the wrong impression, thinking a horizontal asymptote is a line which the graph follows along on both sides, but actually a horizontal asymptote can go strictly to the right. It's just actually the graph, it's basically the line that shapes this curve, or you could say the curve makes an effort to follow that line. Okay, on this side, turns out that we have the same exact behavior, except it's coming from underneath, but we saw that the limit was 0 on this side as well as x goes to negative infinity. So this is just confirming that the x-axis is indeed a horizontal asymptote. But had this part of the problem not been here, we still would have used the phrase horizontal asymptote, and of course we put in the dotted line. Okay, I'm going to do that. Okay, we're not going to draw the vertical asymptote right now because we're not talking about that. We're talking about going out to the right, out to the left, indefinitely. Okay, here's what I was saying about how on either side it could be actually different. This function is a little more interesting. This is the x over square root of x squared plus 1 graph. The domain on this thing is all real numbers because it is not possible to make this denominator 0, because you can't make x squared plus 1 ever equal 0. Also, you cannot make the inside of this negative. In other words, x squared plus 1 is a positive real number. The square root of it is a positive real number. And so we're dealing with completely we're dealing with completely real here. Real number on top, real number interior, and positive, so it can be square rooted. And so we're dealing with a ratio of two real numbers. Anyway, there's no reason to think that there's any domain restrictions. If you did the summer assignment, there was some comments there and some questions about domain. Radicals and denominators can present domain restrictions, but neither of those happen here. Okay, so I'm going to go ahead and put a function in here. We're studying the right-hand side, so we're going off to the right, and you can see here that this is actually approaching 1. This is the y equals 1 line. You can tell from the window description here that this graph goes between 1.5 and negative 1.5 on the y-axis. Okay, and if we're going to the left, so this was at 1. If we're going to the left, we can see that it dips down to negative 1. Same function, leftwards indefinitely. Okay, so your notes are correct here. It should say the lines y equals negative 1 and y equals 1 are, and then it's horizontal asymptotes, plural. So a graph can actually have more than one horizontal asymptote. Okay. There we go. Okay, so what exactly is a horizontal asymptote? We know that. Let's describe it this way. The line y equals b is a horizontal asymptote if, and then it can be either of the following two statements. Either the limit as x goes to infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. So in this case, b was, back on example 1, b was actually 1. Sorry, I won't move it there. So the line y equals, I'm sorry, on example 1, the x-axis was our horizontal asymptote, so b is 0 here. The line y equals 0 is a horizontal asymptote if either the limit as x goes to infinity of f of x equals 0, or the limit of f of x as x goes to negative infinity is 0. And in our case, for example 1, they both were 0. So the b would represent a 0 here. Okay. So some graphs have horizontal asymptotes. Alright, page 2. Okay, back in that previous example, f of x is equal to x over square root of x squared plus 1. We saw just from the graph that we had that behavior. You can also see that from tables. We talked about this before, but this graph, as you go larger in the x values, so this would be considered going x goes to infinity. That's an infinity. You can see what the y is doing. The y is going to 1. Okay, so you could say y equals 1 is a horizontal asymptote. It's not 100% convincing, neither is the picture, actually. We'll have to talk about how to do limits without pictures or graphs to really be 100% sure that that's an asymptote. But from the graph and from the table, it seems to be the case. And then we can see here as x goes to negative infinity, we can see that y goes to negative 1. So you're just following the numerical trend, and you can see that these are getting closer. 0.9864 is closer to 1 than 0.9906 was. And also true for the negatives. Okay, I think that's pretty self-explanatory. You can tell from the table what the behavior of the numbers are on the y column as you progress along the x column. Okay, these properties showed up back in section 2.1, day 2, and they're all exactly the same. The only difference is they use L and M now. Alright, and you want to take this basically from the perspective of the limit as x approaches infinity of f of x plus g of x equals L plus M. And then there's the negative infinity, and that's just the second option. So the theorem would work both ways. Okay, so this is just the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. Okay, and then there's the third one. So I'll move that. And then the fourth one, fifth one, sixth one, seventh one. So what I'd like you to do is just pause the video, go back to your 2.1 notes and fill in the remainder of these blanks. And there's a typo here. This is a multiplication, so this should be a times there. I'll correct. I have that correct on your notes. Just an error on mine. Okay. So once you go and pause the video, come back to it. Okay, so here we are on our second page. We're going to be doing some more complicated functions, finding limits here. We're dropping the f of x and going with just y. Of course, that means the same thing. We have, actually y is used for graphing, just so you know, and f of x is used in function notation. Okay, just a quick recall from example 1, that the limit of 1 over x as x goes to infinity is 0. And that is also true for limit of 1 over x as x goes to negative infinity. You should refer back to example 1 if you need. Okay, we're going to be finding limits both to negative infinity and to positive infinity here for y. This is the given function. So if you recall the rules, we can actually take a limit of a product by doing the product of limits. So instead of working with actual product, let me move this over here. Okay. So we'll be doing x goes. Let's do the infinity first. Okay, so we could work with the entire limit. But one of our rules allows us to split it instead. Okay, so we're going to go from this approach. First we'll do the limit as x approaches infinity for 3 over x minus 1. And then we'll multiply that by the limit as x goes to infinity, and then the second function. So 2x cubed. We're going to split this up into 3 parts actually, over x cubed, and then here we have a 6x over x cubed, and we have a minus 1 over x cubed. And my facts over here from example 1. Okay, we're going to be using that fact here in just a second. Maybe you can already see that. I'm going to try and change my contrast here a little bit. Let's see if I can get that to show up a little better. Well, it's about the best I can get here. Okay, hopefully you can read it. Alright, well, let's take a look at this part. This is basically two limits. We know that this is 3 times 1 over x. So that's essentially 3 times 0, because we saw that the limit of 1 over x goes to 0. So this is just basically 3 times 0. The limit of a constant is simply that constant, so minus 1. Okay, this reduces to just 2, so the limit of that constant 2 is 2. This reduces to 6 over x squared, which is basically, well, it's 6 over x times 1 over x, you could say. So this is 6 over x times 1 over x, both which reduce to 0. So yeah, it's 6, probably the best way to think of it here would be 6 times 1 over x times 1 over x. So that's basically 6 times 0 times 0. And this is 1 over x times 1 over x times 1 over x, all of which are 0. And so we end up with basically 3 times 0 minus 1, so that's negative 1. And then this is 2, and that's 0, and that's 0. So this vanished, this vanished, this vanished, and we end up with negative 1 times 2, negative 2. It'd be interesting to punch this function into our calculator and actually graph it, and we would see that as you go out to the left as far as you wish, you would find that the graph tends to lean towards being at y equals negative 2. Now we could go back through and plug in negative infinity. We can do that mentally here. If we were to change this to a negative infinity, that would not change the fact that this is 3 times 0. Remember, if this is negative infinity, the limit of 1 over x is still 0. So this would still be 3 times 0. That would still be minus 1, because the limit of negative 1, regardless of what's down here, is negative 1. This would still be 2, the number 2. So regardless of what's down here, the answer is 2. This would still be 6 times 1 over x times 1 over x. Both of the 1 over x's shrink to 0 as x approaches negative infinity, just as they did with positive infinity. And basically this is the same. We have 1 over x, 1 over x, 1 over x. They all shrink to 0. So this doesn't contribute again. So we just end up with negative 1 times 2 again, either way. Alright, so even if you did plus or minus infinity, either one, you end up with the same result. Okay, is that always going to happen? Well, let's just say always is a risky word. Okay, so we saw one actually before. If you look back at example 2, we saw that on the left, that was not the case. The graph actually approached negative 1 as you extend indefinitely leftward, and then it approached positive 1 if you went the other way. So we don't want to go with always. Okay, let's go ahead and split this one up into 2 parts, and then we'll find the limit. We'll just go with infinity. We can talk about negative infinity at the end like we did last time. Let's break this up. Remember, with a fraction, a plus b over c can be split into a over c plus b over c. And if there's a minus here, same here. Okay, so we're going to go with 5x over x minus sine x over x. And I'm going to go ahead and cancel the x's here. Okay, so this is simply 5. Okay, we can apply this one right away. The limit as x approaches 5, or excuse me, the limit of 5 as x approaches infinity is simply 5, and that would be the same if this were a negative infinity here. Okay, what about this? We have to be a little bit careful about sine x over x. We did see sine x over x before, but if you recall, down here we had a 0. But we have to be very, very careful here. We cannot apply that same rule that says sine x over x has a limit of 1. This is not as x goes to 0. This is entirely different. Okay, so we're going to have to use a little bit of our common sense here. Sine x is bound to give us values between -1 and 1. It doesn't matter what we use for x, we'll always end up with a value between -1 and 1 inclusive. Okay. On the other hand, creating a denominator of magnitude x and allowing x to approach infinity means that this fraction is going to shrink to 0. The denominator will be huge and huger still, and the numerator will simply be between -1 and 1. Okay, so I'm going to go ahead and write this on top, or sin x like that. This will be multiplied against limit as x approaches infinity of 1 over x. So regardless of what this is, we haven't really talked much about these kinds of limits. This is 0. So it's definitely 5 minus, and then that. So regardless of what that is, this whole part is 0, leaving us with the answer 5. Okay. So there it is. And I recommend you go ahead and graph this on your calculator so you can see what it looks like. Okay, let's go back to let's go to our next example. We're going to go ahead and take this one the same way. Why don't you split that one up there too? So pause the video, separate this into 2 fractions the way we did on this previous problem, and apply the limit to both. You might want to reduce before you take a look at the function. Okay, so hopefully you took a look at that one. So what happened here? By the way, on that previous problem, we forgot to mention negative infinity again. Negative infinity here would not change the fact that this comes out as 5. Also, negative infinity here does create a negative situation here, where you're plugging in negative extreme numbers. But here, whether this is negative infinity or positive infinity, we saw back in example 1 that this is going to become 0. So again, it doesn't matter what that is, that's 0, regardless of whether that's plus or minus infinity. Okay, yeah, so it comes out to 5 either way. That's a plus or minus infinity. Okay, so did you look at this one? This one separates into this fraction and this fraction. Okay, so let's take the limit as x approaches infinity. We're dealing with x sine x over 2x squared. One of the factors of x reduces, and we end up with sine x over 2x plus, okay, and then we have limit as x goes to infinity. In the second one, the 2's reduce, and we get sine x over x squared. Okay, let's go ahead and take a look at this one. Let's factor out the 1/2 here. Just kind of playing around with our various properties. You don't have to, but might as well practice some of them. Okay, so we took out the 1/2. We can leave the sine x here, which is, it's like sine x over 1. Okay, so then we have times, and then limit. Over x. So you can see this is sine x over 1 times 1 over x. That's sine x over x times 1/2. That's 1/2. Or excuse me, that's sine x over 2x. Okay, and then plus. We have limit as x goes to infinity. And this is sine x. Again. Times. And this is 1 over x squared. And one of the things we saw earlier is that this is 1 over x times 1 over x, basically. Okay, so you can get really carried away with this, but that's going to be some number between -1 and 1. I don't know what. In fact, it's impossible to determine. It's definitely something between those two values. This is 0. You keep seeing that. I think it keeps popping up. We also have this part being 0, or excuse me, some undetermined amount. And this part is also 0. Remember that you can... Let me pause here, you can copy this down in a minute. This is basically the limit as x approaches infinity of 1 over x with the square on the outside too. See, we can write it that way. That was one of our properties in the text. Okay, so this inside part 0, we're squaring it 0. So the answer just turns out to be 0 plus 0, which is 0. Okay, now you could have looked back at the original problem and made this, you could have determined this at the very beginning. This is going to be some value between -1 and 1, this portion, the sine x, and this part x will be a very, very large number as x approaches infinity. So we're going with positive infinity here. This is going to be between some number between -2 and 2, because the sine x portion is between -1 and 1. Okay? So it looks like, as you look at the numerator, of all the things that really matter, it's really this x out front. This is just some number between -1 and 1. And this whole thing is just some number between -1 and 1. So altogether, we basically have x on top and some change. Okay, downstairs we have 2x squared. So in the extreme behavior, when x is going to infinity, we basically just have x on top and x squared on the bottom, which is essentially 1 over x, which has a limit of 0 if you go to infinity. Let's check negative infinity on this real quick. Negative infinity would cause this again to be some number between -1 and 1, because the domain is all real numbers. You can plug in negatives here if you like. You still get a value between -1 and 1. This portion with a negative infinity still comes out to 0. This is the same as that. And this part is just simply limit as x approaches -infinity of 1 over x with the square on the outside. This is 0, we said. It's just 0, 0, 0, 0, 0. Okay, so how long does it take to do a limit problem? That depends. That depends on how many of the rules you know. It depends on how much work you're being asked to show, and so forth. Alright, so there it is. Okay, the last page of your notes asks you to see exploration 1 on page 72. There's a series of questions there that ask when we're allowed to and not allowed to use the Theorem 5 properties. And this section of the notes is very, very important. I can't stress enough to you how important it is that you read these things and wrestle with their meanings and answer these types of questions. Can we do this right now? Can we not do this right now? This is what calculus is all about. So you need to be willing to wrestle with this material. You need to be willing to ask good questions. You need to be willing to be called on, and even if you don't know answers, to just let that be. Someone else might have a nice explanation for it in class, but this ultimately is between you and the textbook, and between you and this knowledge. And I know I'm saying it over and over, but really, if this kind of material is not read through carefully, we will not be doing our critical thinking in the first place. And then we need to wrestle with it. So knowing the terminology, being able to read it, being able to really think it through, answer the question, have a justification for it if you think the answer is no, to explain it. We would like to be using full sentences here, so you might be called on when this lesson is covered in class, and maybe you can have a good way to explain things for us here. Okay, and don't forget down at the bottom to be recording things that you memorize, special cases, etc. We did learn a couple things about asymptotes you might not have known about there being 2 horizontal asymptotes, but find your own facts to memorize.